As for our last lesson in chapter 2, and this is kind of where we put it all together. We're going to be looking at graphing rational functions. So a lot of this will be material that's put together from previous sections with one new piece of information called slant asymptotes or oblique asymptotes. So we'll talk about that as we get into the lesson. But let's take a look and see what we can remember and work with in these problems and do a little warm up here. So first, we're going to try to graph this function up here. We're going to try to graph that function knowing what we know already. And we've already determined that it's a little easier to be able to graph these by hand if we can have the function factored into factor form. So that's what we're going to do. And on the top part of this, we're going to factor that trinomial. And again, why we spent that time at the beginning of the school year working on factoring. So we should know that this factors into two binomials. We got 2x and x. And then we're going to play around with factors of -5. So really the only ones are like -1 and +5, or could be +1 and -5. But when I do this one, I do get the 2x squared for the first part. When I do multiply the outsides, I get 10x. The insides -1x. That gives me the 9x. And then the last, -1 times 5. Does give me that -5. We'll do the same thing on the bottom. We'll factor that trinomial. This one's a little easier because the leading coefficient is 1. So we just simply look for two numbers and multiply, give me -20, but when added, give me +1. So we'd have x plus 5 and x minus 4, because the 5 times -4 gives us -20, but when added gives us +1. So this will help us set up some of the other issues that we have down below in terms of finding the x-intercepts, y-intercepts, holes, vertical asymptotes, horizontal asymptotes, as we progress through this problem. So what we got to remember now, when we find x-intercepts, that's always where the y value is 0. Okay, so that's just a good thing to always remember. Because what you do then is you just simply say, well, when is this function going to be 0? Well, if I look at this as a one big fraction, to be at 0, the top has to be 0. The numerator has to be 0. So in this case here, either the 2x minus 1 or the x plus 5 has to be 0. So if this is 0, I don't care what that is, I multiply it, it should be 0 on the top. So it's just a matter of setting each of these individual pieces equal to 0. So just setting this first one, 2x minus 1 equals 0, and if we add 1 divided by 2, x equals 1/2 is a 0. A solution, a root, those are all synonyms. And this other one, x plus 5 equals 0, subtract 5 from both sides, x equals -5. These are the two x-intercepts, or roots, or solutions, or zeros. Those are all synonyms. Then, as we progress into the y-intercepts, now remember, to find y-intercepts, that's when the x is 0. Okay. So we're simply going to put 0 in for the x's up here in the equation. So we're basically doing f of 0, putting 0 in for that x right there. So it'll be 2. Actually, we can make it a little bit easier here. We'll do it in this function right here. So we'll say 2 times 0 minus 1, and then 0 plus 5. I guess you could have done it certainly in the other one as well, too. And then down here, 0 plus 5, 0 minus 4. And as we see this would be -1 on the top times a +5. So that'd be a -5. And on the bottom here, we've got 5 times a -4, which would be a -20. And then negative divided by negative is a positive, so this would be 1/4. So our y-intercept would be where y is 1/4. Now again, if we're talking about intercepts, we should have had these as coordinates. So our x-intercepts here would be at 1/2, 0, and -5, 0. Okay. And then our y-intercept here would be at 0 and 1/4. Okay, so that'll help us when we do some of the graphing. Okay. So now let's find the holes. Now remember, when we find holes, that's where factors cancel out. So if we're looking at our original equation up here, that's been factored. This f of x equals 2x minus 1, and then x plus 5 all over the x plus 5 times x minus 4. We see these are the ones that get canceled out, the x plus 5. So we take that canceled out factor, set it equal to 0, and that's where we have a hole, is where x equals -5 on the graph. So we'll remember that and how to graph that too. Okay. Vertical asymptotes are where the denominator is 0. That doesn't factor out. So it's this one that's left over here. So we just take x minus 4, set that equal to 0. X equals 4. That's where we're going to have a vertical asymptote. So remember, that's that vertical line where we have discontinuity. This is a spot, a coordinate on the graph where we have discontinuity. We have removable discontinuity here. Okay, so we'll have to graph that and find out. We'll have to look where that y value is, but it's where x is -5 on the graph. All right. The horizontal asymptotes. Okay, as we start looking at these other pieces, let me go back up and rewrite the original equation here. So that was f of x equals 2x squared plus 9x minus 5 all over x squared plus x minus 20. So remember now, the horizontal asymptotes depends on these leading coefficients. Okay? So some of the things to simply remember with our horizontal asymptotes is that, and we'll review this on the next page, but if the denominator has a larger degree, there's a horizontal asymptote at y equals 0. If they're the same as we have here, then we have to look at that ratio, this 2x squared over x squared, they're the same. Look at the ratio of those coefficients. So that ratio, that coefficient is 2. So in this case, we would have a horizontal asymptote at y equals 2. Okay. And then we'll discuss too about when the numerator degree is larger than the denominator, we won't have a horizontal asymptote, but we will have what's called an oblique or a slant asymptote. Yeah, so we'll talk about that in the next page, because that's the new piece. Part G, state the end behavior using limit notation. Well, what I do know is I do have a horizontal asymptote at y equals 2. So we know that in the graph here, 1, 2, that as as the graph itself would move this way, as the x's go to infinity, whether it's on the top or the bottom of this, it's going to be approaching that 2 value. And same thing on this other side. If we go to negative infinity, whether the graph's in the top part of this or the bottom part of this, we know it's got to approach that 2 value. So what we'll say here is that the limit of this function as x approaches negative infinity, that it's got to go to 2, okay? And that the limit of the function as x approaches positive infinity, so as x goes out to positive infinity, it too will level off there at 2. And then the last thing, just to kind of review, is to be able to state the domain. This is where you can use some, that test point kind of idea. If you look at that horizontal line. We do know from earlier that we do have a hole at -5 and an asymptote at 4. So that means we can't have a value at -5 and we can't have a value at 4 because we've got either a hole or a vertical asymptote here. So our domain, those are the values it can't have, but it can take on everything else. So we'd have to say our domain starts over here at -infinity, and that's always a parentheses when it's next to infinity. And then again, we can't have -5, so that just has to have a parentheses as well. We're going to then unite that with this middle part, which is from -5 to 4. So again, parentheses because I can't have that value. And unite with everything on the right side here. So from 4 to infinity. All right. Well, let's just kind of write some highlighting notes here just for you so you have these. And the first thing we should always do when I kind of think about coming to the important pieces here is you should factor first. And that's what we did right here. Okay, oops, down here. Is get that into factored form because it helps us identify those pieces a little bit quicker. And as we did here with the x-intercepts, so I'll say to find x-intercepts, set y equal to 0. And we can do this for the next piece here. For the y-intercepts, to find y-intercepts, set x equal to 0 and solve. Other piece as we go down here for holes and vertical asymptotes. Remember, holes are where factors cancel. And vertical asymptotes are where the denominator is 0. And then we'll talk about those horizontal asymptotes. So I'll say, you're going to do this in the next page here, so I'll just say see notes on next page. Basically what I want to do is just highlight that and just say that, if, the degree, so let's look at a fraction here. So if the degree on the denominator is larger than the degree on the numerator, so we got a smaller degree on the numerator and a larger degree on the denominator, we'll have a horizontal asymptote at y equals 0. If they are the same, okay, so you have the same highest degree on the numerator as we do on the denominator, then what we'll have is y equals the ratio of the leading coefficients. And then if the degree is larger on the top than it is on the bottom, and this is where the new piece will come in. That's what we'll talk about in the next page, is we have a slant asymptote. I guess officially could also be called oblique asymptote. Okay? Either one is called that way. So we'll talk about how to do that on the next page, but still trying to get through some of the review pieces here just to make sure we get it. So just kind of want to talk a little bit about this limit stuff like we did over here, and look at some of our more complicated graphs of rational functions. And in this one here, if we do have vertical asymptotes, we'll actually have you have 2 on each side, because you'll have a limit as the graph comes in, and as I'm coming in and then approaches this asymptote from the left side or from the negative side, we have to talk about where that's going. Same thing this on the right side of this vertical asymptote, we got a graph that's coming in from the positive side, and we got to talk about what's happening there. So for example, if I'm looking at the limit of this function, let's just call it f of x. And then as x approaches this -2 value from the left side, so what we indicate that is put a little negative up there on the top. So it's saying x approaches -2 from the left side. So as I approach -2 from the left side, the graph here seems to be going down forever. So it's going to go down to -infinity. The limit of f of x as x approaches -2 from the right side, so I'm going to approach -2 from the right side here, it will go up to infinity. Well, we also have an asymptote here at +2, so we've got to address that one as well. So when I look at the limit of the function as x approaches +2 from the left side, so as I approach +2 from the left side, this graph is going down. That's down to -infinity. But as I take the limit of the function as x approaches 2 from the right side, so I'm going to approach 2 from the right side, this graph is going up to infinity. So we have to look at that behavior if we have vertical asymptotes. All right? That's not called end behavior. It's just a type of limit as we approach points of discontinuity. So the end behavior, we'll look at what's happening, out here and out here in this area as the graph goes out, as the x's go out to infinity or the x's go out to -infinity. So that's where we just say the limit of our function as x approaches -infinity. So as I approach -infinity, as I go this way, what's the graph doing? Well, it looks like it's going here and kind of leveling off at that 0 line, at that horizontal asymptote. So I would say 0. And then the other way, the limit of the function as x approaches +infinity. So as I go this way, what's the graph doing? Well, the graph looks like it's leveling off at 0 as well. Okay, so there is a little bit of review and a warm-up for our 210. So let's do, like I've been talking about here, let's go in and talk a little bit about these horizontal asymptotes and review that concept and teach you the new piece about over here, as you see, about oblique or slanted asymptotes. Okay. So again, as a quick review, if we look at our function and we see that there are there's a greater exponent in the denominator than there is in the numerator. Okay, we can kind of parse that out and just look at those pieces that have 2x squared and 5x to the 4th. Those are the highest ones. So even if you wanted to cancel this out a little bit just to see, that would cancel out 2 of them. So I really have like 2 over 5x squared. So you can see the top wouldn't change at all, but the bottom would keep getting bigger and bigger and bigger. So therefore, this fraction is actually getting closer and closer to 0. So that's why we say y equals 0 would be our horizontal asymptote in this case. Anytime, again, the denominator's degree is larger than the numerator. So sometimes we call this just bottom heavy. So if you're bottom heavy, your asymptote will be at y equals 0. Here, again, we're looking at the highest degree for each of these expressions in the numerator and the denominator. And again, if I just parse that out, I get 4x squared over 2x squared. And if you do simplify this, this would come down to just be 2. Well, again, when they are the same, our horizontal asymptote is y equals whatever that reduces to. So y equals 2 would be our horizontal asymptote. In this problem, what you see is that the numerator here is larger than the denominator. So this is what we call top heavy. Okay? When it's top heavy, there is no horizontal asymptote. And that's what we learned in the past. But what's new now is we do have what's called, again, an oblique or slanted asymptote. And that's what we got to learn how to do. And we didn't have these skills the first time we talked about this, but now we do. And that's where we're going to use long division. But you could use synthetic if I was dividing by a linear factor. But in this case here, you can see I'm not dividing by a linear factor, I'm dividing by a quadratic factor. So we're forced to use long division here. So I'm going to take that 2x squared plus 3, and I'm going to divide it into that numerator, which is 4x to the third. And oops, got to watch out here. We're missing a term, because we've got to make sure we have that placeholder. So plus 0x squared, because we don't have a squared term, and then plus 2x minus 1. All right, so when I do that, then I'm looking at, well, what do I multiply 2x squared by to be 4x to the third? Well, I'd multiply it by 2x. I'm going to line it up over here. All right, and then take 2x times each of those pieces. So I get 4x to the third, and then 2x times 3 would be 6x. So I'm going to add that over here. And then remember to change the signs. Falls out, that's just 0. 2 and negative 6 is negative 4x. Bring down the other one. Now you notice here I can't take 2x squared into x. So this would actually be the remainder. But we just can ignore that in terms of finding our oblique asymptote or our slant asymptote. Because what we're going to look at is really just this piece then. And our slant asymptote is y equals 2x. And again, don't worry about that remainder piece. So this is just here, our slant asymptote. So you can see that's an equation that's got a slope of 2. So it's not a horizontal line. Okay. All right, one little more piece here just to kind of review and make sure we understand some pieces before we do one big problem. Let's take a look at those vertical asymptote pieces. Okay. It says there are two possibilities for the middle part of the graph. It's either parabolic or it's S-shaped. So, for example, I might have a graph that looks like this. Let's just say here's my y-axis, but maybe I've got a vertical asymptote here, and I've got a vertical asymptote here, and then maybe I've got a horizontal asymptote right here. Okay? So what we're talking about here is that I might have a graph that's in this part right here, and it's doing this. Got another part over here that's doing this. Now, what they're saying here, there are two possibilities for the middle part of the graph. So they got this middle part in here. One option would be that it's parabolic. So maybe I've got, parabola in here. Okay. Or the other option, if I draw another graph here, and draw the same thing here. So we kind of got a vertical asymptote here, and here, and a horizontal one here. So maybe you're going to have a graph that's maybe coming in like this, one that's like this. So again, that middle part could either be a parabola, can be drawn up in any of these portions. But now this one might be a S-shaped or lane change piece. So this middle part, that we have here can either be a parabola or a lane change. It can either be an even function or an odd function in there. The outsides will still be hyperbolic, having those branches from a hyperbola. Okay, or an inverse model or an inverse square model, they're also sometimes called. So again, what we'll do is we'll use that test point method that we learned in a previous lesson to decide how the branches are drawn. Okay. Sometimes I'll say just be a little careful not to just look at just the signs, but to look at the numbers as well too. And that's really important when you have horizontal asymptotes that are not y equals 0. Okay. All right, so let's play around here a little bit. And let me just give you a function here. So let's go f of x equals x minus 1 all over x squared minus x minus 6. Okay, so now remember, always our first step should be is to factor this. Okay, so the top, still x minus 1. There's nothing really I can do with that, but factor that denominator. And if I do that, I get x and x. The two numbers multiply give me negative 6, but give me negative 1 when I add. So I'd have a factored function there. So what I can do really quick here then is again then look at our leading terms. And from that, I can see the denominator degree is larger than the numerator. So that tells me something. That tells me that I have a horizontal asymptote at y equals 0 because my denominator's degree is bigger than my numerator. What I can also then here too tell is that I'm not going to have any holes in the graph because I don't have any factors that cancel. But I do know that I'll have vertical asymptotes. Okay? And I'll have vertical asymptotes if I set each of these equal to 0. So x minus 3 equals 0. So x equals 3 would be a vertical asymptote, and then the x plus 2 equals 0. So I have vertical asymptote at negative 2 as well. Okay? So other things I want to do in helping me find and be able to graph this is to be able to find those x-intercepts and the y-intercepts. So now remember, to find those x-intercepts, we're just going to put 0 in for y. So what I'm looking for then, if I put 0 in for y, I'm looking to solve that 0 equals x minus 1 all over the x minus 3 times the x plus 2. So I want to know, when is that 0? Well, that occurs when this part is 0. So that's really all I got to look at is, when is x minus 1 0? Well, it's when x equals 1. So I will have an x-intercept at 1, 0. Okay. For the y-intercept, and to find that y-intercept, remember what we do is we put in 0 for x. So we're basically finding that f of 0. So in this function right here would be 0 minus 1 all over 0 minus 3 times 0 plus 2. So that would equal negative 1 on the top. This is negative 3, and that's a positive 2. So that'd be negative 6, which reduces just to 1/6. So I have a y-intercept at 1/6. So that would be at 0, 1/6 is where my y-intercept is. All right. So in setting this up now, what I want to look at is taking these points, putting them on just a using this test point method just to figure out how I'm going to start to graph this. So again, this horizontal line, I got to think about where are the points of discontinuity, where are the things that I can't have. So I know that I can't have values at negative 2 and 3. Okay, so there's negative 2 and there's positive 3. These are vertical asymptotes. So again, I can't have them. I can't have those values up here. I also know I got an x-intercept at 1, 0. Okay. So that's, because I'm going to just draw it arbitrarily, that's 1. Well, I can have that. That's actually the actual x-intercept, so I can have that. So I'm going to put a little solid dot right there. Okay. And that's using some test point methods. I'm going to look to see, how I might graph this. So again, I'm going to probably use this part of the function as in factored form to help me go through this a little faster. So let's just pick a point here. Let's just pick like negative 3. So I've put negative 3 back in that equation. I get negative 3 minus 1, which is a negative number. right there. There we go. Over, put -3 in there. -3 is -6. That'd be a minus number. And then -3 plus 2, that's also a minus number. So I'd have a negative number over two negatives, which is a positive, so negative over positive. So negative over a positive is a negative, so I know that this answer here has got to be negative in this area. From -2 to 1, probably an easy number to pick there is 0. So I put 0 in there. That'd be a negative number on the top, negative and a positive. So altogether, this would be a positive number in there. Let's pick the number 2 here for here. So 2 minus 1 is 1. That's a positive number. 2 minus 3 is a negative number. 2 plus 2 is 4. It's a positive number. So this would be negative in that area. And then here, let's pick a number. Let's pick the number 4. 4 minus 1 is a positive number. 4 minus 3 is a positive number. 4 plus 2 is a positive number. So this would all be positive. Okay. So in doing all this now, this should help me make my graph. Okay, so we'll get this sketched in here. And maybe start doing some of the easier pieces first here. Let's get those asymptotes in. So I know I've got a horizontal asymptote at y equals 0, so just maybe kind of draw over this so you remember that. We got that horizontal asymptote there. Our vertical asymptotes at 3 and -2. Okay, so let's just go 1, 2, 3, 1, 2, 3. And I have vertical asymptote at 3. And the vertical asymptote at -2. All right. That's going to help me line things up here. I also know that I'm going to cross here at 1. Okay, so I do know that that's going to cross here. The graph's going to cross at 1. It's also going to cross at 0, 1/6. So maybe if I just draw this at 1, it's at 2. So if we can do some labeling here, that's 1, 2, 3, -1, -2, -3. This is at 1. This is at 2. So maybe I should just draw these down here too at -1, -2. So I then know it's going to cross at 0, 1/6. So that's like right here. Okay. I do know that here at -2, the graph's got to be in the negative area. So again, at the ends, remember we talked about it being branches. So it's got to be right here is a branch. We know here at the end over here too. At the ends, it's got to be a branch. Right? So this one's got to be all in the positive area. Right? So I'm going to draw that in there. Now in here, this is how we can kind of see if it's going to be a parabola or if it's going to be a lane change or an S shape. We know here before 1, it's positive, so it's got to be up here. After 1, it's negative. So that's where it makes that S shape. It's got to be positive here before the 1, but then negative here after the 1. And that's the way our graph should look. All right, let's try putting it all together, doing it one more time. This one didn't have a slant asymptote in it, so let's introduce that piece to our final problem. Okay. So what we're going to do is we're going to graph this function right here. Right? So I'm going to go through all of our processes. And remember, always, 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 always factor first. It makes your life so much easier. So if I take f of x and I factor this, the top really doesn't change. It's just x to the third. Okay, this is a difference of perfect squares, so we know that that's x plus 3, x minus 3. Okay. So there's our factored form. It should help us with these pieces. So again, now if we're going to find the x-intercepts, that's where we say that's where y equals 0. So we're solving this for 0. Where does this function equal 0? So x to the third over x plus 3 x minus 3. So again, where it equals 0 is where the top has to be 0. So really what we're doing is just trying to solve where 0 equals x to the third, because for a fraction to be 0, the top has to be 0. And if I just simply take the cube root both sides, I can get x equals 0. So that means the x equals 0, and the y is 0. My coordinate for the x-intercept is at 0, 0. Okay, so might as well mark that point here since we're there. Let's put that point right on our graph. Okay. Let's find the y-intercepts. Again, to find the y-intercepts, you substitute x equals 0 into our function. So if we do that up in the top here, so f of 0 equals 0 cubed all over 0 plus 3 times 0 minus 3. 0 cubed is 0. The bottom here, this would be 3 and negative 3, so negative 9, which still is just 0. So looking at our coordinate, that's 0, 0, that's our y-intercept as well. Well, that kind of makes sense. If 0, 0 is an x-intercept, it's also a y-intercept. If I continue, and I'm going to rewrite this down here now as we progress and go back and forth, our holes, remember now, with our function, we have f of x equals x to the third over x plus 3, x minus 3. So again, remember, holes occur where there's factors that cancel, so there aren't any. So there are none. There aren't any holes in this graph. For the vertical asymptotes, again, we look at where does the denominator become 0. So that's either where x plus 3 equals 0 or x minus 3 equals 0. So there's a vertical asymptote at x equals 3, and negative 3, and x equals positive 3. So let's go back in there and draw those guys in. Okay, so if we assume that every square is a 1, this is a 1 by 1 square. This is still 1, 2, 3. So we got a vertical asymptote right here. And then one at negative 3. All right. So let's go down here and see if we can find any horizontal or oblique asymptotes. So again, if we look back to our original function, f of x equals x to the third over x squared minus 9, we notice that the numerator degree is higher than the denominator. So there are no horizontal asymptotes, but there is an oblique or slant asymptote. Remember, how we find that is actually by doing this division. And again, at the bottom, if we're dividing by a linear factor, we could use synthetic division. Well, we don't. We have a squared here, so we have to use long division. So I'm going to take x squared minus 9 and take that into x to the third. So we'll need all our placeholders here, so plus 0x squared plus 0x plus 0. And then I look at, well, what do I multiply x squared by to be x to the third? And I just multiply that by x. So to multiply that by x, I get x to the third. X times minus 9 is a minus 9x, so we'll line that up there. And then remember to change the signs. Goes away. Here I get 9x plus 0. Well, I can't take this into here, so I will just ignore that remainder. And then there's my slant asymptote. Y equals x. That is my slant asymptote, or again, oblique asymptote. So I can put that in my graph here as well too. I graph this. Y equals x would just be up 1 over 1, up 1 over 1. As I keep graphing that, or if you go down 1, left 1. So it would be this as a slant asymptote. Right, so those are points of discontinuity. So let's look at how to graph this graph now with some of these parameters that are set up. And again, using the test point method is the best, and that's what we've been teaching. So let's give that a try. So what I do know here then is that if we use the test point method, I know I can't have a value here at -3. Again, that's going to be an open circle on there because you can't have that. There is a point here at 0. I can have that actually. And there's a point here at +3. But I can't have that. So we're going to test these different areas, these 1, 2, 3, 4 different areas to see what happens in those functions based on our original function. Let's write that off to the side here. Y equals x to the third all over, I guess it would be a factored function, I should say. And look at how it behaves. So if I put a number in here like -4. -4 to the third, well, that'd be a negative number. Okay. In fact, let's even just use some numbers here. So -4 to the third is -64. Put -4 in there, that's -1. -4 in there is -7. And what I'm saying, yeah, -4 and -7. So if I put that in there, I get -1 times -7. And so roughly here, this would be a negative over a positive. So I know I'm going to get a negative number in here. And so -4 over -64 over 7 is a little over 9. Okay. So this would be approximately -9 point something. Okay. So in other words, I got a negative number. Okay. So let's look at a number here. Let's look at, say, putting -1 in there. If I put -1 in there, and -1 cubed is -1. This is -1 plus 3, which would be 2. -1 minus 3 would be -4. So this would be a positive number, so I know I got positive here. But this would be 1/8. Take the positive 1 here, so I put +1, I get 1. 1 plus 3 is 4. 1 minus 3 is -2. So here I get -1/8. So I get a negative number in this area. And if I take a number bigger than 3, let's just put 4 in there. 4 to the third, again, is 64. 4 plus 3 is 7. 4 minus 3 is 1. So again, this would be a positive number. And again, this is roughly a little over 9 point something. All right, so kind of this helps us with our behavior in terms of graphing this up above here. Okay, so let's see if we can get that scrolled back up here. So I know in this area from -3, I got to be in the negative area, so I got to be everything below. So now I can't be up here because, yes, this is negative in this area, but it does get to be positive here. So I got to keep myself into this negative area. So our graph will kind of come in like this in that little quadrant there, because that would all be negative. It would all stay negative in terms of our y values here. So again, I couldn't draw it in here as a branch because it does go positive. I only want it to stay negative. Here now we got this middle part, so remember it's either going to be a parabola or it's going to be a snake, an S-shaped. I notice here it goes from positive, and then when it gets to that x-intercept, then it goes negative. So this has got to be one of these pieces that snake through. And I guess it did, when I look at this, it's going to come in, and snake in like that, and go down like that. Again, going through that y-intercept there, that x-intercept as well. Then I know from here, from 3, it's always got to be positive. So again, I can't draw the branch in this area here because it would go negative. So I got to keep it into this little area right here and have it drawn in that little spot. So that's how our graph looks. And if we're going to answer some of the last questions, I want to be able to state that domain. Okay, so state that domain. I can still use this to help me here, because I know then that the graph here, this goes out to negative infinity. We have our first kind of point of discontinuity at -3, so it's going to go all the way up to -3. Can't touch that because it was an asymptote there, so I'm going to put a parentheses there. I'm going to unite that with, now it goes here from, I could break this down to 0, but that's not a point of discontinuity. That's just an x-intercept. So I don't need to break that apart. I can kind of combine these two, so I know my domain will go from -3 up to 3. And again, using parentheses because those are bordering on the asymptotes. And then the last piece is going out from 3 to infinity. So if I'm going to describe the end behavior now, again, I'm going to look at this end behavior. So I'm only looking at the pieces that are out here and out here. Okay? I'm looking at what happens as x goes to infinity and as x goes to negative infinity. So here, as x goes to negative infinity, this graph is going down. Okay? And here, when x is going to positive infinity, the graph is going up. So I'm going to write those down. The limit of this function as the x goes to negative infinity, again, I'll look back up here. As x goes to negative infinity, this graph is going down. So going down to negative infinity. The limit of this function as x goes to positive infinity. Okay, so again, as x is going to this positive infinity, this graph is going up. Okay, so it'll be going up to infinity. And then we have the behavior near the vertical asymptotes. So we should have, since we have 2 vertical asymptotes here, I should have 1 from each side here and 1 from each side over here. So I'll eventually have 4 different limits here. So I have a limit of f of x as x approaches, I think my asymptotes here were at -3 and 3. So we got the ones that will approach -3 from the negative side, and then the limit of f of x as x approaches -3 from the right side. And then I'll also have the limit of this function as x approaches +3 from the left, and the limit of this function as x approaches +3 from the right. Okay, so 4 different limits to evaluate here. So here, if I go back up and look at the function and look at how am I approaching -3 from the left. So as I approach -3 from the left, so here I've got to go down to where the graph is. As I approach -3 from this left side, the graph looks like it's going to go down to negative infinity. As I approach the graph, as I approach -3 from the right side, so here I'm coming in from the right side, and as I approach the -3, it looks like that graph is going to be going up to positive infinity. And then let's look at as I approach +3. So here's +3 is right here. And so as I approach +3 from the left side, it looks like it's going down to negative infinity. And then as I approach 3 from the right side, so again, as I'm coming from the right side here, so I can look at the graph. As I approach 3 from the right side, the graph is going up to positive. All right, well that gives you some examples of how you can do some graphing by hand of our rational equations, and give you a little chance to practice and ask some questions. So we'll see you in class for that. Thank you, everybody. Good luck on the Chapter 2 test when it comes.